So our project is basically based on application of wireless sensor network in precision agriculture. As we already know, India is an agriculture-based country where 69% of the Indian population has agriculture as their main occupation or side business. The traditional methods of farming are not so efficient. So, for increasing the yield, by adopting for increasing the yield, we can adopt different advanced technologies of modern farming, such as precision agriculture. Precision agriculture employs data from multiple sources to improve crop yields and increase the cost effectiveness with crop management strategies, including fertilizer inputs, irrigation management, and pesticide application. Basically, the architecture of precision agriculture system is based on wireless sensor networks, which consist of large number of different sensors, which can be placed in a field and construct a self-organized network to monitor the value change, including the temperature, humidity, atmosphere, precipitation, and soil pH value. This data collected is sent to the sink by wireless mode to the agriculture control centers, in which integrate sensor data, providing farmers with the ability to identify the fields that require treatment and determine the optimum amount of water for the soil growth, the fertilizers, the pesticides to apply. So this can help the farmers avoiding resource wastage and preventing runoff, ensuring that the soil has just the right amount of additives for optimum health of soil. So a report has description of design and implementation of wireless sensor networks made for monitoring agriculture environment and evaluate the reactivity, robustness, and longevity of the network. Talking about the crop, we have taken chili plant as a main crop for precision agriculture. The main advantages of chili plant are as following. Basically, chili plant has a wide range of adaptability. It can withstand heat and moderate cold to some extent. The growth of chili plant is far faster and it can attain a maturity about in 45 to 60 days. It does not require any special land preparation. It does not require any special soil type. Basically, it can be grown throughout the year. It does not specially require any kind of special weather. It is a low cost crop and low cost crop, and it does not require additional large expenditure for the growth, and it does not require a large amount of insecticides and pesticides as compared to the other plants such as tomatoes. Talking about chili plant growth requirement, especially for the climate requirement, chili is a tropical and subtropical plant which requires a combination of warm, humid, and dry weather. Basically, the temperature requirement of chili plant is in a range of 20 degrees to 25 degrees, being the ideal temperature. It can be grown over a wide range of altitudes, and it is generally a cold weather crop. But it can be grown throughout the year under irrigation. About the soil requirement, it can be grown in wide variety of soils, with the soil pH requirement being 5.5 to 6.8, and soil being rich in organic matter and well drained. Land preparation for chili is of no any special land requirement needed, and chili crop generally requires fine tilth with the for the land, and it requires plugging of about 2 to 3 times. The growth rate of chili plant is generally fast. It's a fast growing crop and usually attains for maturity in 45 to 60 days, and the cost requirement being not very large. The nursery bed preparation should be of 1 meter width, 40-meter long, and 15 centimeter of height to be ideal. And if there is one more than one seed bed, so we should make a wide canals of 30 centimeters for drainage purpose. And the seed rate is also not very high, and it just requires in 1 acre about 650 grams of seed. Now, here in our project, we have taken a square-shaped grid in which there would be 28 plants per row and column each. Now, spacing requirement for single plant, approximately 32 centimeters of spacing has been given for the project. And for talking about the intermode spacing, there would be modes taken at 1 meter horizontal and vertical gap from each other, with the mode being attached to the plant for sensing.
So coming to the deployment pattern, we have deployed our crops in the form of a square structured grid as shown in the figure. And here the red nodes show the modes which are having the ultrasonic sensors. The blue mode shows the chili plants with yellow Z modes, and the orange one shows the chili plants with the mica Z modes. And the small triangles, green triangle, shows the chili plants. So this is the whole deployment, and this is the base station here. So there will be 28 plants in each row and each column, and similarly 10 modes in each row and column. So there will be a total of 100 modes, out of which 36 will be Mikaze modes and 64 will be Talosmi modes. Now coming to the spacing, based on the research done on the growth patterns of chili plants, we have kept a distance of 32 centimeters between every two chili plants, and between the two modes the spacing is of 1 meter. So coming to the requirement of sensors, for microclimate measurements we'll be using temperature and humidity, light sensors, and soil moisture. So temperature and humidity and light sensors are present on the Talosmi itself. And for intruder detection, we'll be using ultrasonic sensors. Now coming to the proposed hierarchy, as we discussed, the deployment is done in the structured square grid, and we have divided the whole structure into small 9 clusters. Now we are opting for cluster formation because it will allow data aggregation and deduplication also. Also, it helps in the formation of a route from a node to the base station and vice versa. Now, since every node forwards its data to the cluster head, this helps in reducing energy consumption as compared when every node passes on its data to the neighboring node and so on. So, as we discussed, there will be 9 clusters in which there will be 4 Mikaze nodes, which are in this orange colors, and rest will be the normal Talosmi nodes. We also have a rotation policy in our network, like after every fixed interval of time, like suppose 10 minutes, we will rotate the cluster head, and this cluster head will be re-elected among the Mikaze modes only.
Now I'll be discussing about time synchronization for a precision agriculture project. Time synchronization in all the networks, either wired or wireless, is very important because it allows for successful communication among nodes within the network. The time synchronization protocol that we'll be looking into for our project will be TPSN. TPSN is basically sender to receiver type, that is, sender attempts to sync all the receiver. And it generally happens in two different phases. The first one is level discovery phase, and the other one is time synchronization, which happens just after the level discovery is done. TPSN is generally self organizing in nature, that is, different levels are going to be automatically discovered. But according to our deployment pattern, levels are inherent into our network as the position of all the nodes are fixed. Hence, levels are decided on the basis of transmission range, and no level discovery phase is required as such. Our deployment is hence divided into levels, clusters in each level, and nodes within the clusters. Here, base station will be acting as level 0. Deviation protocol will have to be run every hour so as to ensure that nodes maintain the same time. When talking about the working, it is very simple. Initially, base station will be broadcasting time information to all the cluster heads of the cluster in level just above it. That is, base station will send the time information to the cluster head in the level 1. The cluster head will be chosen on the basis of the energy. Then these cluster heads, which are chosen on the basis of the energy, will not only broadcast this time information to the nodes within their clusters, but also to the cluster head of the level just above it. And this will further keep carrying on to the last cluster is reached or the last level is reached.
So as per the project requirements, we are required to send the periodic data as well as whenever a query arises from the base station, the data has to be sent. Therefore, the routing protocol which we find most suitable is APTEAN. APTEAN stands for Adaptive Team, and APTEAN is able to combine the best features of proactive and reactive networks while minimizing their limitations to create a new type of network called the hybrid network. So in this network, the nodes not only send data periodically, but they also respond to sudden changes in the attribute values. So first of all, the nodes are grouped into clusters, with each cluster having a cluster head. This cluster head aggregates all the data sent to it by its members and forwards it to the upper cluster head, and so on till the data reaches the base station. Since the cluster heads perform the functions that consume more energy and to evenly distribute energy consumption, clusters exist for an interval called the cluster period T, and then new cluster head is elected. This happens at a time called the cluster change time. In Aptene, once the cluster heads are decided in each cluster period, the cluster head first broadcasts the following parameters. Attributes. This is a set of physical parameters which the user is interested in obtaining the data about. So in our case, that will be temperature, humidity, etc. Thresholds. This parameter consists of a hard threshold and a soft threshold. Hard threshold is a particular value of an attribute beyond which a node can be triggered to transmit data, whereas the soft threshold is a small change in the value of an attribute which can trigger a node to transmit data again. Schedule. This is a TDMA schedule similar to the one used for assigning a slot to each node. Count time. It is the maximum time period between two successive reports sent by a node. It can be a multiple of the TDMA schedule length, and it accounts for the proactive component. Main features of this protocol are by sending the periodic data, it gives the user a complete picture of the network. It also responds immediately to drastic changes, thus making it responsive to time-critical situations. Hence, it combines both proactive and reactive nature. It also allows the flexibility, or it offers a flexibility of allowing the user to set the time interval and the threshold values for the attributes. Energy consumption can be controlled by the count time and the threshold values. For example, if we set the threshold values towards the lower end, the nodes will send the data more frequently, hence energy consumption will increase. Whereas if we send the threshold values to a higher end, therefore the nodes will send the data more frequently, hence the energy consumption will increase. The main drawback of this protocol is basically the additional complexity required to implement the threshold functions. In query modeling, to handle the queries efficiently, it is assumed that nearby nodes can sense similar data, and hence we can form pair of two nodes and only one node will respond to a query. The other node can go into sleep mode. Therefore, these two nodes can alternatively take the role of response handling queries. In our deployment diagram or in the deployment pattern that we have, this node present in the level 3 will send the periodic data towards its cluster head. This data will be forwarded by the cluster head of level 3 towards the cluster head of level 2. This then will be forwarded towards the cluster head present at level 1 and finally to the base station. Now, whenever a query arises from the base station side, it will be forwarded to the level 1 cluster head and then to the level 2 cluster head. Now suppose let we our target node is in the level 2. Therefore, the level 2 cluster head will send the query towards the destination node. The destination node will respond to the query, and an exact reverse path will be followed by the data towards the base station. So this is how the routing protocol for Aptene will work.
I will discuss about sleep-wake pattern. Here we are using modified TDMA for scheduling the sleep-wake pattern of the nodes. As you can see in the diagram, the whole network is divided into clusters, and in each cluster we have the level. So like the base station is at level 0, then cluster 1, as you can see it is in level 1, the lower levels are level 1, then level 2, then level 3. So we have defined the levels also, and in each cluster we have cluster heads and the cluster members. The yellow one are the cluster heads, which are the yellow ones are the potential cluster. Only one can be the cluster head at a time, and all other nodes are the cluster members. So in the first time slot, let's say this node is the cluster head and all other nodes are the cluster members. So let's say according to the TDMA, this node will send its data and this node will sleep. After this node will send this data according to its time slot and this node will sleep. After that, this node will send its data to its cluster and it sleeps. Similarly, in all other clusters, the cluster member sends its data according to its time slot, and they will sleep. So the cluster members can sleep after sending its data, and they will wake up after the after some periodic time interval, and they will send its data. After this, now the now we will go to outside the cluster. So in this, where this cluster has the data, so this cluster sends its data to the this cluster head in the level 2 cluster head. Like we have assumed here that we have three level hierarchy, and we are assuming that we have vertical hierarchy. So level 3 sends its data to level 2, and from level 2 to level 1 in the particular time slot. Here cluster head will always listen for the query, so they will always remain awake. So from the level 1 we have the level 0, but in level 0 base station there can be collisions. So we have defined the another time slot for the base station. So for, like, let's say in the first time slot in the base station, cluster 2 will send its data, then this cluster head will send its data, then this cluster its head will send its data. So by this we by this there is no contention for the base station, and there is also no collision of the data. So in the first time slot, as you can see, these are the sleeping nodes, which are the channel members. So in this time slot, the channel members send this data. After this, the channel head sends in data, which are the ideal nodes, and after this, the channel head to the base station. So this is the modified TDMA.
I will be explaining about the intruder detection. As you can see from the deployment diagram, these red color modes placed on the borders are used for the purpose of the intruder detection. These modes will never go to sleep. They will always be on. But in order to prevent early dying out of these modes will not evolve in the process of sensing and communicating the periodic data. So the data or the environment close to these nodes will be sensed by the neighboring nodes. As our network is overly deployed, so this will not affect much our network. Now each of these nodes are interfaced with the ultrasonic sensors, which is HCSR04, and this sensor has maximum sensing range up to 400 to 450 centimeter, and this sensor will be monitoring continuously. Now, whenever the intrusion is detected at either of the borders, the node will detect this intrusion and inform about this intrusion to the nearest cluster head, whichever is the closest to it. And this cluster head will in turn inform about this intrusion to the base station. So the intrusion has been successfully informed to the base station.